Okay, so you can tell that this is a buffer because I have something that has an H in the front, so that's my weak acid, and then I have a salt here, something on the left side of the chart with something on the right side of the chart. So this is definitely a buffer problem. And I've got another way to show you how to work it, but it's sometimes helpful for these for you to see a familiar method first. So I'm going to use an ice chart on this one, but then I'm going to show you how you can bypass the ice chart in the next section. So I am going to write the K expression for this one. This one I'm not going to be able to find a K expression for because it's not the acid one. So I'm going to write the HF, and then I'm going to write it reacting with water, and it's going to make H3O plus F minus. Now you'll notice that NaF and F, those are the same thing. We call those a common ion, and that's going to come up again later. So just letting you know, this common ion word, if it has something common in it, then you can substitute some of this one in. And this is how we do it. So we take 0.82, that's my initial amount. Wait, before I get going, the reason I have the left side up is because I need the HF value. So let me scroll and grab that one. There it is. I put it at the top. So the Ka expression is F minus times my H3O plus over my HF. And I know that that term is 6.4 times 10 to the minus fourth. And I know that that's what this is all equal to. So I'm just rewriting this so it looks a little neater. All right, so now what I'm going to do is I'm going to fill in my ice chart. Scooch that over, make the screen bigger. So prior to buffers, what you do is you say, okay, this is 0, that's 0. And then the water, of course, that one doesn't matter, so you don't put the water in. That one is minus x, and because all the coefficients are all 1, that's plus x, and then that's plus x. Now, what's different when I have a common ion there is that I actually can put it in this term. That's what happens. It's basically in solution, I've already got some H. It's already in, some F. It's already in there. Since NaF has only one of these, so I've got a 0.1 and 1 liter, I can say that in 1 mole of NaF, I have 1 mole of F. And so that just shows me I've got that same molarity, but it's just for the F. So that's what I'm putting in this problem. Now, what I'm going to do is I'm just going to solve 0.82 minus x, 0.51 plus x. And when I plug it in, I get 6.4 times 10 to the minus fourth equals 0.51 plus x, and I am going to get rid of that x in a minute, times x over 0.82 minus x. And remember that x, it's like saying, Dr. Bean's theme is, it's like saying, if I've got $1 million and you give me a few dollars, do I still basically have $1 million? And the answer would be like, yeah, you do. So here's how I'm going to solve that. I'm going to just go ahead and say that x is way, way smaller than both 0.51 and 0.82. Like it's way smaller, so I'm going to throw it away. I'm not throwing away the x that's outside of the parentheses. So like that was in parentheses times x. I'm not getting rid of this x. That one has to stay. And then I've got that 0.82 is what I've got left over here. So I'm going to pull up my calculator because remember I'm solving for x, and that will give me my H3O, which will then get me to my pH. So 6.4 e to the minus fourth, and then I need to multiply both sides by 0.82. And then I'm going to divide both sides by 0.51. So I'm going to do that. So times 0.82 divided by 0.51. And that gives me that my x value is 0.00103. I'm putting a few extra digits in there. Molarity. And if we weren't sure if it was okay to make that assumption, remember, I take the number in my calculator, I divide it by, I'm going to divide it by that number. It's the smaller of the two. So that number divided by 0.51 0.51 and times 100, and as long as that's under 5%, I'm okay. And that's under 5%, so I'm good. I was totally okay to make that assumption. So I've got this term right here, and that is my H, and if I want to turn into pH, then I would just say that my pH is, I'm going back to this, the negative log of that number, that 0.029 number, 0.00103. And so that gives me, you can see it rounds up, it's going to be that my pH is 2.99. And again, like I said, I just did the negative log. You should be really comfortable with this, equals my pH, and then I've got my pH right there. So this method right here, a lot of people feel really comfortable with it, and I think it's a great method. There's nothing at all wrong with it. It also introduces common ion, which we'll see again next week, but there is a faster way, and that's what you're going to see in just a minute.